Good afternoon. Thanks to Mitch Sams for encouragement, Denny Siglo for the images that will relieve the verbal monotony, and Matthew Barisi for taking on the challenge of teaching an old man new presentation tricks. Janet was concerned that I might speak too long. I assured her that each viewer is equipped with an off button to escape. For my captive viewers, you are now aware of the lengths to which I'll go to secure an audience. The explosion that shook the world. My title today is Volcanoes, Vulcanism and Climate Change. I invite you to join me as I explore a topic that has fascinated me for over 50 years. My story starts in an unlikely setting, a class of 7th grade Sunday school students in November 1967. In a discussion of the differences between myths, fables, and parables, I dismissed Atlantis as a myth and was called on it by Bobby Judd. Mr. Yost, I've just read that it isn't a myth. And the following week, he brought me an article from that source of all scientific wisdom, the Reader's Digest. An article describing the explosions of the island of Thera in the Aegean Sea, an island better known to us as Santorini. You're looking at the illustration that introduced the article. A term of geology in college to satisfy part of my science requirement had given me enough background to appreciate the story. It stimulated a continuing interest in geology, leading me into archaeology, dendrochronology, and now volcanoes. Originally their impact on our history, now expanding into their impact on our climate. To assist our understanding of volcanoes, in 1984, scientists Newhall and Self created the Volcanic Explosivity Index, VEI, by which they assign relative explosivity values from 1 to 8, based on 3 criteria. First, the estimated volume of ejecta. Second, the eruption's cloud height. And finally, qualitative observations. The 1980 eruption of Mount St. Helens on our west coast is ranked a 5. Thera, which erupted in 1626 BC, is ranked an 8. Above the VEI ranking of 2, the scale turns to logarithmic increases. And 8 represents a cloud column height of over 66,000 feet and an ejection of tephra of 240,000 cubic miles. But the VEI index tells only part of the story. What else is in that volume of ejecta? It does not tell us the amount of gases blown into the atmosphere, such as SO2, sulfur dioxide, nor of HO2, 2 primary contributors to climate change. Unfortunately, no such index guides us to the impact of these gases and others on our environment. When the volcanic explosion's plume rises through the troposphere into the stratosphere, the gases and particulate are carried by winds around the world, as Mitch has explained to us. And for the largest volcanic explosive eruptions, across the equator as well. We'll examine the historical record of several eruptions going back to 2000 BC for their impact on climate, both locally and around the globe. But before we preview specific volcanic events, we need to understand the process that fuels these eruptions. For our understanding of plate tectonics, we can thank Alfred Wegener, who first published his theory of, quote, continental drift in 1912. With the subsequent accumulation of evidence from multiple scientific sources, by 1960, plate tectonic theory had gained widespread acceptance as the model of Earth's processes. For our visits to selected volcanoes as we go back in time, we'll stop at areas where plate boundaries create the conditions to fuel volcanoes and volcanism around the world, particularly the Ring of Fire that surrounds the Pacific Ocean. The diagram in front of you shows the hot spots at the top, and so on. Then we move on to tectonic plates. We'll identify types of plate boundaries. The island of Iceland is the product of the, quote, divergent tectonic process, where plates are moving in opposite directions, giving magma easier access to the surface. Hidden under the Atlantic Ocean is the mid-ocean ridge, dividing North and South America from Europe and Africa, with the divergent tectonic process driving us further apart. Along the mid-ocean ridge, only Iceland protrudes above the ocean surface. Onto the Cascadia volcanic arc. The volcanoes which dot our Pacific Northwest coast are the product of the convergent process, as the Juan de Fuca plate is subducted under the North American plate. Subduction, a fancy word for the fact that the Juan de Fuca plate slides under the North American plate. The process generates the volcanic activity along our Pacific Northwest coast. The red triangles denote volcanoes from British Columbia to Northern California. Mount St. Helens in 1980. The eruption, rated a 5 on the VEI index, is fueled by the subduction of the Juan de Fuca plate. This is a small but very active segment of the Ring of Fire. We'll hear more about this eruption later on as we compare the output of different volcanic eruptions. We're traveling on to Indonesia. The red dots on this image are Indonesia's collection of volcanoes, more than any other country in the world. And why is that? A 2016 news clip caught my eye and identifies the forces involved. Quote, the global positioning system, we know it as GPS, is no longer working properly in Australia. Tectonic movements have pushed the entire continent about 5 feet north of where it was 20 years ago. Australia is sliding northwest at a rate of nearly 3 inches a year. Its tectonic plate is sliding under the arc of Indonesia's islands, fueling their volcanic activity frequently and disastrously. We'll visit Krakatoa under the D in Indonesia and Tambora to the east under the I in Indonesia. More specifically, we're now looking at a map of the Sunda Strait between Sumatra and Java. Krakatoa, which erupted in August of 1883, rates a explosivity index of 6. And it shows, the map shows 3 eruption sites in this Sunda Strait region. Krakatoa's 1883 explosion is the middle one, an eruption well documented. Please read Simon Winchester's book for the details. The VEI rates the event as a 6. For a while, I was puzzled by the absence in the record of any impact on the weather to the east across the southern Pacific. Then the light dawned. The obvious answer is that there's almost nobody in that vast expanse of ocean east of Indonesia until you come to the west coast of South America. I'm indebted to our Jim Green for detailed stories of the impact of Krakatoa and its eruption recorded in his family's history in Watauga County, northwest North Carolina. Brilliant sunrises and sunsets, unusually cold weather. The impact of the volcanic dust in the atmosphere lasted 5 years, shielding the earth from the sun's rays. But bad as Krakatoa was in 1883, the 1815 eruption of Tambora produced a substantially greater impact. Tambora, 1815, raises the explosivity index to 7. Years ago, reading George Condon's Stars in the Water, the story of the Erie Canal, published in 1974, I came across the following passage which imprinted on my memory. Quote, "For some strange meteorological reason, the year of 1816 had been one of unrelieved cold weather. Winter had lasted all summer long. At the time, I didn't realize I was reading about the impact of Tambora's 1815 eruption. Condon cites Storrs Barrows, an amateur meteorologist, who, quote, kept a careful, chilling diary, from which I share these excerpts. May, oh, how chilly. Buds and fruit were frozen. The 18th day, Colonel Hicks planted his corn the second time with an overcoat and mittens on. Corn was planted and replanted until anticipation of a crop were no more. June. This was the coldest June ever known in this latitude, north 33 degrees, 10 minutes. There was a sprinkling of snow on the 25th. Sharing my interest in this topic with Professor John Garver, head of Union College's geology department, he reported that in 1816 it had snowed on Union's June graduation ceremony. Continuing with Storrs' diary, August, if possible, was more disagreeable and cheerless than the summer months already gone. The 16th ice was formed as thick as window pane. Almost every green vegetable was destroyed. The story of the year-long winter remained with me. Bill Bryson's description of this event in his, quote, A Short History of Nearly Everything, one of my resources, expanded my understanding of the wider impact of this eruption. He writes, quote, crops everywhere failed to grow. In Ireland, a famine and associated typhoid epidemic killed 65,000 people. In New England, The year was known as 1800 and froze to death. In 1985, a Smithsonian article titled "Concentric Clues from Growth Rings Unlock the Past" started me down another path of exploration into dendrochronology. The article introduced me to Andrew Ellicott Douglas, who arrived in Arizona in the 1890s to find a site for a new observatory. In 1901, he started examining tree stumps for evidence of 11-year sunspot cycles and observed that the pattern of thick and thin rings were consistent across northern Arizona in the stumps he examined. Studying live and dead bristlecone pine trees in the high Sierras along the California-Nevada border, we now enjoy a continuous record of tree rings going back 9,000 years as a result of the efforts that Douglas started. Douglas' work led to the foundation of the Laboratory of Tree Ring Research at the University of Arizona in Tucson in 1937. In the early 80s, researcher Valmore Lamarche in Arizona, quote, looked at the tree ring record and described frost rings in the bristlecone pines and determined that a number of them seemed to correspond to major volcanic eruptions. Tambora's 1815 eruption was not only felt in New York, but, quote, on trees Lamarche studied in South Africa, unquote. The article continued, trees remember, and scientists are learning to ask them about everything from historical dates to earthquakes and volcanic eruptions. And now we're going to travel to a favorite destination. Janet and I hosted an Icelandic Lutheran minister and his family in 1963, starting a friendship that continues to this day. We spoke with Bernardur Gudmundsson and his wife Randve just last Sunday. I confess that 2 visits involved chasing Atlantic salmon. I now wish I'd paid more attention to Iceland's geology and volcanoes. We're now looking at the map of the mid-Atlantic ridge as it crosses Iceland. And indeed, it's a hotspot for volcanic activity. Its very existence, the result of repeated volcanic eruptions along the mid-Atlantic ridge, where the tectonic plates are pulling apart. As far as I know, you can still stand astride the ridge's rift in Iceland's Ting National Park, with one fort ready to move to Europe and the other toward Greenland and North America. You should plan for a long wait. We're talking geological time. Now we are looking at Iceland's volcanic zones. And it should be no surprise to you that Iceland's areas of volcanic activity follow along the mid-Atlantic ridge. But we're going to turn to the Loki Fissure in Iceland. And this is our example of volcanism, a low level of lava and gases that had none of the explosivity that we assume with volcanoes, with little of its eruption reaching into the stratosphere. Even though the eruption continued over 8 months in 1783 and 84, its VEI rates only a 4. The eruption from its 15-mile-long fissure started on June 8, 1783, with 5 intense bursts during the first month of its 8-month activity. The results were widespread. You're looking at slides depicting the impact over our northern hemisphere. First of all, the eruption's impact in the lower atmosphere across Europe was widespread, with a dense veil of cold fog during the summer of 1783 and the extremely severe cold the following winter. Ben Franklin, in a paper dated May 1784 and delivered to the Literary and Philosophical Society of Manchester in December 1784, speculated, quote, whether it was the last quantity of smoke long continuing to issue during the summer from Hekla, also in Iceland, which might be spread by various winds over the northern part of the world, is yet uncertain. An Economist article on this eruption and its impact on Iceland is titled "The Summer of Acid Rain." The author writes that the gases expelled by Laki were 80 times greater than those expelled by Mount St. Helens. Lacking the explosivity of Mount St. Helens, 3/4 of Laki's expelled gases remained in the lower atmosphere and produced a vast plume of acid rain brooding over the skies of southern Iceland. The article continues, in the normal course of events, prevailing winds, as we have learned from Mitch, would have blown the poisonous plume toward the Arctic. But the summer of 1783 was not normal. A stable ridge of high pressure had settled over northeast Europe, pulling the winds in the Laki cloud southeast towards the European mainland. By the end of July, Laki's impact was being felt in Moscow, Syria, and points further east. The devastating rain had catastrophic results in Iceland. The spread and extent of the dry fog was felt across Europe. As a result was an extremely hot summer, followed by an extremely cold winter. And the U.S. did not escape, enduring, quote, one of the longest and coldest winters with temperatures almost 5 degrees Celsius below average. And in Charleston, South Carolina, the harbor froze hard enough to skate on. Now we're going to journey back to the Indonesian Sunda Strait. But now we're back to an eruption in 535 AD. Its explosivity index is unlisted, at least not that I could find, but I'm assigning it an 8. So when someone starts talking about Krakatoa, I ask, which eruption? I had chanced on a book titled Catastrophe by David Keyes, published in 1999, which explored the sequence of events that ushered in the Dark Ages. In Catastrophe, Keyes documents his thesis of a colossal volcanic explosion with an impact on mankind's recent history far greater than any other natural disaster. He summarizes as follows. In AD 535-36, mankind was hit by one of the greatest natural disasters ever to occur. It blotted out much of the light and heat of the sun for 18 months, and the climate of the entire planet began to spin out of control. The result, direct or indirect, was climate chaos, famine, migration, war, and massive political change on virtually every continent. Key's thesis proposes the mystery climatic disaster of 535-36 AD resynchronized world history, unquote. He goes on to quote the Roman historian Procopius. The sun gave forth its light without brightness, like the moon during this whole year. In Britain, the 20-year period starting in 535, quote, saw the worst weather that century. He cites heavy falls of snow in Mesopotamia and in Arabia. Famine followed by flooding. In China in 536, there was drought and famine. And, quote, yellow dust rained down like snow. Quote, in North America, analysis of ancient tree ring evidence in the western region of the US has shown that some trees there virtually stopped growing in the years 536 and again in 542 to 43, and that normal growth patterns did not reoccur until some 23 years later in 559. Keyes goes on to describe the plague that swept up out of Africa into the Mediterranean and on up into Europe. He describes the domino effect of famine-induced migrations, which start in Mongolia and arrive in Europe to encounter a weakened Roman Empire. And after military successes, exact a tribute of gold from Rome. Keyes devotes substantial evidence to the changes wrought in Western Europe by the famine created by the natural disaster, and the plague which followed hard on its heels. Tree ring growth in Great Britain slowed significantly in 535-36. The plague arrives in 540. In a relatively short time, the population in southwest England is reduced by 60%. In the Far East, the events are amplified in the written record. The reference to yellow dust comes to us from the history of the southern dynasties of China. Its occurrence beginning sometime between November and early December in 535, continuing with frost in July and snow in August, ruining the crops. Now it's time to find the culprit, the cause of such widespread disaster and misery. Keyes examines and discards the possibility of an extraterrestrial asteroid or comet impact. Convincing evidence comes from two ice cores drilled in Greenland in 1978 and 1990 in the form of acid-rich snow, falling more than 2 years in one core and for at least a year in the second. Corroboration comes from a distant source. A core drilled in Antarctica reveals acid snow fell for a period of at least 4 years. Now we have the evidence of a truly colossal volcanic eruption, but where is the source? Reading Keyes for his deductions was a delight. He employs a highly skilled form of direction finding to locate the source in the tropics and in the Java-Sumatra complex. The Chinese history of the southern dynasties comes to his aid, recording a vast explosion in February 535 AD. Quote, there twice was the sound of thunder coming from the southwest to Nanjing, the South Chinese imperial capital. Keyes focuses attention on the area we already know as the site of Krakatoa's eruption of 1883. Once again, the written record helps us along with a story from the Indonesian Book of Ancient Kings. It describes the huge volcanic event in the Sunda Straits area. and concludes saying, when the waters subsided, it could be seen that the island of Java had been split in two, thus creating the island of Sumatra. Keyes concludes, this geological evidence, when combined with Chinese historical, Javanese quasi-historical, ice core, and other evidence, makes the Sunda Straits caldera, Proto-Krakatoa, the most likely site of the 535 super eruption. And since that date, we now have further published scientific results of the Greenland ice cores in the Geological Society of America's special paper 505, to which I was introduced by Bruce Hobbs. Cross-dating 3 ice cores, quote, found a Tambora-sized sulfate peak for which they estimated an age of 533 to 534, plus or minus 2 years. The paper's author, Adrian Jones, is still undecided as to whether this event is of volcanic origin, extraterrestrial, or a combination. I had a chance to ask the volcanologist Nelia Dunbar whether in comparing dates from ice cores and tree rings, to which I should give greater credence. Tree rings, she answered. We'll pass by Vesuvius, which erupted in 79 AD with a explosivity index of 5. It's so very well documented, and many of you have enjoyed the Bay of Naples, Pompeii, and or Capri, so I shall spare you further discussion of its eruption. And we'll move on to Thera's caldera and its eruption in 1626 BC. I hope many of you have had the thrill of sailing into Thera's caldera to visit Santorini, located some 70 kilometers north of Crete in the Aegean Sea, and to walk the excavated streets of Akrotiri. The caldera is roughly 4 miles wide and 8 miles north to south, and as I've recently learned, may be hiding 2 calderas, not just one. This image of the Eastern Mediterranean, titled Ash Deposits, comes from that Reader's Digest article in 1967, and describes the ash deposit from Thera's eruption, spread across the Eastern Mediterranean, giving me an early sense of Thera's wider impact. Then we come to my favorite source, the Science Times, and its continuing articles. Returning to dendrochronology, one particularly severe set of frost rings occurred in 626 BC, and Lamarche suggested that the rings may have been caused by the destruction of the island of Thera and by a volcano. And this gives me the opportunity to return to my Sunday school class. I'm intrigued with the possibility of a connection between Thera's eruption and the Bible stories of the plagues that descended upon Pharaoh and the Egyptians, as described in Exodus. At the end of Exodus, chapter 13, verses 21 and 22, I read that, quote, and the Lord went before them day by day in a pillar of cloud to lead them the way, and by night a pillar of fire to give them light to go by day and night. He took not away the pillar of the cloud by day, nor the pillar of fire by night from before the people. Here ends that brief reading. Our current understanding of Thera's eruption suggests the possibility of an extended eruption, with the output of smoke and ash creating the climatic conditions which cause the plagues. The list catches your attention: frogs, lice, flies, cattle dying, boils, plagues, and pestilence, unusual rain and hail, and finally locusts. As a source of scientific detail, I'm quite disappointed in the author of Exodus. Surely he heard the cataclysmic explosion of Thera's magma chamber when its weakened walls collapsed from the pressure of the surrounding Aegean seawater. I imagine a colossal boiler explosion. Perhaps a diligent Egyptian scribe on a tablet yet to be unearthed recorded more of the impact of Thera's eruption. Thank you for joining me of this visit to various volcanoes and for the opportunity to share these stories with you. Good afternoon.